Hello and welcome to Learning Git. I'm Sam Slotsky and I'll be your guide for this course. As a software professional, I've used Git exclusively for over half of my career and have authored and contributed to open source projects using Git as well. And I'm here today to show you how flexible, powerful, and incredibly useful this tool can be. In this multi-part screencast course, we'll learn concepts that will familiarize us with different aspects of Git, from the core basics to collaborative teamwork, and on to a few advanced features like squashing commits and tagging releases. To start things off, let's review our objectives. By the end of this course, you should be able to see your repository from initialization all the way through to a production release and learn a few advanced features along the way. This begins with creating a repository on your local machine, committing some changes, and pushing the changes to remote repositories. Here we'll also discuss different authentication protocols for communicating with your remote. After that, you learn to capitalize on some features designed for team collaboration. This involves creating feature branches for independent features and work streams, as well as creating forks and submitting work via pull requests to keep the main repository protected. Once we're introduced to the concept of forks, we'll learn some techniques for keeping our forks up to date with any changes made to the upstream repository. Finally, we'll see some advanced features that will help us keep our local commits small while keeping history cleaner and more concise on the remote, as well as tracing commits to see who wrote code and when. Some notes before concluding our first video. In order to follow along in the course, you should have the Git command line utility installed, as that's how we'll be demonstrating most of Git's features. OS X users will need to have the Xcode command line tools installed to have access to this program. Most Linux distributions should have it available through the system's package manager, like Yum or app. For Windows users, the GitHub client for Windows is available on the web and comes with both a GUI and a command line utility. I also recommend downloading PowerShell and running the Git utility from there, as this will match the command line environment we're using much more closely than the DOS shell. Join us for our next video, where we'll get an abstract explanation of what Git version control is and what it's used for. Hello and welcome to Learning Git. We're now in our first section of this course in which we're getting an abstract introduction to Git. In this section, we'll set some goals for the course and then take some time to discuss what Git is, which involves some general discussion about distributed version control. And we'll also talk about different types of workflow and how to choose the one that's right for you. For our first video in this section, we will explain what Git version control is, starting with a brief overview of the concept of version control and moving into what makes Git stand apart from many other systems, and how that's advantageous in a collaborative environment. So what is version control? Version control is a tool that allows you to keep a history of changes to your content. When used for computer programs, each history entry typically represents a working version of code. The history will show us who made changes, when they were made, and why. And perhaps most importantly, a version control system can merge conflicting changes when two different team members modify the same content. To see why merging is so important, consider a project where multiple team members are working together to write a simple poem about a bird. Imagine that instead of using version control, the content is stored on an FTP site and each team member can download and then upload when finished modifying. Now meet Bob and Mary, two of the project's team members. As you can see, each one has added a different line of text to the poem. Whoever uploads the file to the FTP site first will have his or her changes overwritten by whoever uploads second, so the change will be lost. A version control tool will detect this problem, however, and will let us choose from a few possibilities of how to deal with this. Typically, the options are to keep only the first change, keep only the second change, or apply both. So if all version control systems accomplish tracking history and merging conflicting code, what is it that makes Git different from other systems? For starters, the fundamental concept of a commit is completely different from a centralized version control system, or CVCS. In many other systems, a commit only represents the changes that were made to the code. With Git, as well as other distributed version control systems, each commit represents a snapshot of the entire project. As an example, consider this commit as shown on GitHub. Here we see a list of modified files and their changes, which is what we'd expect to see from any versioning system. Note, however, the Browse Files button on the top right. Right now, we're looking at all of the project files, exactly how they were when the commit was made. That's because a Git commit actually describes the state of every single file in your project at that point in time. Additionally, with systems like Git, developers are working on actual clones of the repository. This means they have access to every commit in the project's history on their local machines, including all divergent branches. This is drastically different from a CVCS, which only gives developers the copies of the files as they were at the point in time specified in the checkout request. So what's good about all that? In fact, you will likely find it useful in myriad ways, but here are some big ones. For one thing, multiple clones means multiple backups should an outage occur in the intended central repository site. Secondly, it also means that developers can work offline if they need to and still make small commits, which is essential to productive development and version control. And as we'll see later, distributed control means we can set up multiple independent work streams so different team members can work on different features or areas of the application without having to worry as much about what the rest of the team is checking in. This concludes our introductory explanation of Git version control. In our next video, we'll look at some of the different workflows that are possible with Git and consider how to pick the right one for your project. Hello and welcome to Learning Git. We're wrapping up our introductory quick start section where so far we've already established some goals for the course and had a brief overview of what Git is. In our last video, we learned what Git version control is, focusing on the central aspect of distributed control. For the last video of this section, we'll talk about choosing a workflow that's best suited for your development team. One great thing about Git is its flexibility of workflow. There are countless ways to organize how changes will eventually make their way into the master branch, so teams are really free to choose what's right for them. There are a handful of commonly used ones, though, and today we'll talk about 3 of them: a centralized workflow, a feature branch workflow, and a forking workflow. While Git was built to be a distributed version control system, using the same type of centralized workflow that you would find in a CVCS like Subversion or Team Foundation server is still perfectly possible. Team members simply pull and push from the master branch and never create additional branches. But since we work on clones of the main repository, we still get the benefit of being able to make small commits while offline. As an example, let's consider our friends Bob and Mary from the last video. Mary's working offline while she waits for her car to get fixed and makes a few small local commits. But Bob has checked in a few commits to the central repository since Mary last pulled down the code. When Mary gets back online and tries to submit her work, she discovers that her branch has diverged from the main repo. When this happens, Mary needs to incorporate Bob's changes. Since Bob beat Mary to the central repo, the commit history should reflect this. Mary would use the rebase feature, which will pull Bob's work and then apply hers on top of that. A centralized workflow like we just described might work perfectly for a smaller team, but in larger projects this is going to require frequent synchronization to keep divergences manageable. A feature branch workflow will ameliorate this situation and will also keep the master branch clean and functional. With this kind of setup, each feature goes into a dedicated branch in the central repository, with each branch diverging from master at a different point in time. Work for that feature can be accumulated into that branch until it's ready to be merged into master. At any point during that process, a pull request can be submitted that shows the difference between the feature branch and master, allowing for discussion of the branch and code review. Here's an example of a pull request I made to an open source project. Right now we're viewing all the code changes. If I click on Conversation, we see a history of this pull request, including some comments made by me and other contributors so the changes could be discussed before it's accepted. Once approved by the repository maintainers, the feature branch can then be merged into master. The last type of workflow we'll discuss is known as the forking workflow and is most commonly used in open source projects. In this scenario, each developer has a copy in his or her own dedicated online repository. This is known as a fork. Here we can see my fork of the repository where I submitted the pull request we just looked at. Notice on the top it says, forked from Exegy Minimongoid, and underneath the branches drop-down, it tells me that I'm quite a few commits behind the original repository. That's because a fork knows where it came from and can track any divergences between the repositories. In a forking scenario, write access to the main repo is restricted to maintainers only. Developers push commits to their own forks and can then make pull requests to the central repository where administrators can decide whether or not to merge the changes. So far, we've seen what Git version control is and the different types of workflows available to us in Git. That completes our first section for this course. Now that we have a grasp on the fundamental concepts, we're ready to start getting our hands dirty in our next section where we'll initialize our first Git repository. Hello and welcome to Learning Git, our screencast course on the Git version control system. In our last section, we learned about what Git version control is, focusing on the central concepts of distributed control and the different workflows that it allows. Today we'll begin our second section where we'll walk through all the steps of building a Git repository. We'll begin by looking at what occurs when a repository is initialized. Then we'll make our first commit, push our changes to our remote repository on GitHub, and explore some of the options available when looking through the commit history. For our first video in this section, we'll focus on repository initialization. But before we dive in, I want to introduce you to a new friend. His name is Zach, and he just had an idea for a real handy app and has the coding skills to make it happen. But he can't do it all alone, so he's hoping to leverage the open source community to make his dream a reality. Zach has heard of Git's popularity for projects like these and has decided to give it a try. Before he can get the code out to other people, though, he'll need to install Git and initialize his repository. Zach's operating system provides a command line tool for Git through its package management system. If you're following along at home, you may want to pause here and visit the Git SCM website where you can find out how to download Git for your specific operating system. To begin, Zach is going to create a new directory with the name that he wants to give his repository. During development, Zach will refer to his project by the code name Finnegan, which is what he'll name the repo. So let's make our directory and step inside. Now that we're here, we simply use the git init command to initialize. We've just created a local repository that we can use to track our changes. Before initialization, our directory was empty, but if we view the hidden files, we see a .git directory. This contains a number of files that define the current state of our repository. Here we can find information about all the available branches, tags, references, and much, much more. We won't go into the details at this time, but essentially, this is what makes your directory more than just a collection of files. These entries allow your directory to reflect the state of your project at the point of any given commit on any branch in the entire history of the repository. This, of course, does us no good unless there are files to track, so let's begin to explore what happens when we start adding files to our project. Since this will be a Ruby project, our first file will be a Ruby class. Zach's app specializes in solving problems, so the first thing he'll need is a problem solver class. So we'll open up problemsolver.rb, and we'll create a skeleton for one of the project's core classes, and save and exit our text editor. Now that there's a brand new file in our initialized repository, it stands to reason that Git should know about it. To see what Git has to tell us about our recent change, we use the git status command. As you can see, the file that we just added is under a section labeled Untracked Files. When Git detects a file that is not in the repository's database, it will list it here. As long as this file remains untracked, it cannot be committed. Since we obviously want to track this file, let's tell Git to do just that with the git add command. Now that we've told Git that we want to track this file, let's see if it tells us anything about our new file. As you can see, our file is now in a section called Changes to be Committed. Any file in this list is located in what's known as Git staging area, which contains all the changes that will be made to the repository when the git commit command is used. In our next video, Zach will make his very first local commit while we talk more about the staging area and the Git repository along the way. Hello and welcome back. We're partway through our second section in this course in which we're currently following our friend Zach as he builds his first GitHub repository. In our last video, we learned what occurred when a repository is initialized. For our second video in this section, we'll see Zach make the first commit to his repo, discuss a couple of relevant commonplace practices, and get a better understanding of the working directory, the staging area, and the repository. Zach will start by making changes in his working directory. He'll then need to move them to his staging area and commit them. You may recall that last time Zach created a skeleton for his problem solver utility and started tracking it. He has made one small change to his code, and he wants to make his first commit before he gets too deep into development so he gets the benefit of versioning from the beginning. Before he does this, he's going to complete a couple basic steps that are common across most Git projects. First, he'll create a readme.md file. Most of you have probably encountered README files before. For Git, this is where we put information about our project, such as a description of what it does, system requirements, installation and running instructions, or notes on how to contribute to the project. The .md extension means that the Markdown syntax can be used to add formatting to the file. Zach hasn't learned Markdown yet, but intends to format his README in the future, so he's going to use the .md extension. For now, he'll just add a vague instruction to install Ruby. Next, we'll edit the git ignore file. This is a hidden file that can be found in many repositories. It serves as a list of all the files that you don't want to check into version control. An example might be if you keep the data for your application in your project directory. Since there's no reason to keep your data in source control, you'd ignore that directory here. Zach's text editor creates a lot of temporary files with the .swp extension. He doesn't want those checked in, so he enters star.swp into the file. Zach has what he needs now for his first commit, but before that he wants to review his changes. Let's see which files Git tells us about when we ask it for a status. There are 3 lists here: a list of untracked files, a list of changes not staged for commit, and one for changes to be committed. You'll also notice that 2 of these lists contain a file with the name problemsolver.rb. So what's going on here? Well, last time we added the file using git add, which prompted Git to begin tracking the file and moved it into the staging area. But Zach has made a change to that file since then, and we haven't told Git that we plan to commit those changes. Thus, we see 2 different versions of the file, one from our working directory and another in our staging area. In this case, running git diff on this file should show us how our working directory version differs from the one in the staging area, so let's give it a try. Here we can see all the code that's been added to the problem solver class since the skeleton was defined. Zach is satisfied with the changes and he's ready to commit. First, he'll add all the files to the staging area. Using a period as the argument to this command tells Git to add every change it detects to the staging area. Now Zach will commit the change with git commit. The -m flag stands for message. Each message should be a concise explanation of what change was introduced, making it that much more important to have very focused commits. A commit explains when a change occurred, who changed it, and why. The first 2 questions are answered automatically, as Git records the author and the date whenever we make a commit, but the reason for the commit is something we must specify and make every effort to do so meaningfully. After entering the command, we see output verifying our changes. And now Zach has made his very first commit for this project. The files Zach checked in started out in what's known as the working directory. They moved into Git's staging area when he told Git to track them, and once he committed, those files became part of the repository. To understand these a little better, let's watch Zach gear up for one more commit. First, Zach is going to change some code. He opens his text editor to the problem solver class and adds a method stub. Then we'll save and exit our text editor. And just as he did before, he'll tell Git to add everything using a period as an argument to git add. Let's try to do a diff and see what changed. With no arguments, you can see that Git doesn't detect any differences, and that's because it's comparing the working directory with the staging area, which are currently identical because we've added all of our changes. What we need to compare against is our last commit. In Git, this is known as head. The word head is one of many references, or refs, in Git. A ref refers to a certain commit on a branch. While some refs always refer to the same branch, head will always point to the last commit of the branch you currently have checked out. So Zach wants to compare his working directory with head, But first he remembered that he wants to add one more method stub. Zach opens up his text editor and adds yet another method stub, and saves and quits. Without even adding the file to the staging area, Zach types get diff with head as the argument. Notice that this time we see both method stubs, even though one is in the staging area and one has not yet been staged. To understand this, think of the working directory, the staging area, and the repository as three different snapshots of the codebase. The repository has all committed changes. The staging area represents the repository plus additional changes, and the working directory represents the staging area plus even more changes. Using get diff is asking for the difference between the working directory and the staging area. Adding head as an argument asks for the difference between the working directory and the tip of the current branch of the repository. If we want to see just the second method stub that wasn't added to the staging area, we can do that by not using any arguments for the get diff command. Now we see every difference between the working directory and the staging area, which is just the second method stub that Zach added since his first commit. In our next video, Zach will push his changes up to GitHub in our video on managing remotes. Hello and welcome back. We're partway through our second section in this course, in which we're currently following our friend Zach as he builds his first Git repository. In our last video, we watched Zach create his README and gitignore files and make his first commit. For our third video in this section, we'll learn about remote repositories as Zach puts his code up on GitHub in order to share with future collaborators. First, we'll get a brief overview of what a remote is. After that, we'll see how to create one and push changes to it. Then we'll talk briefly about our authentication options. So what do we mean when we say remote? In this case, the term is actually short for a remote repository. It's really just a copy of your project that's hosted on the internet somewhere. They are typically found on GitHub and other well-known Git hosting services such as Bitbucket, Beanstalk, and Codebase, although technically any computer can act as a remote Git server. Your local repository can link to as many remotes as you want, but in any collaborative environment, there will be one main remote that is the effective central repository, where everyone's changes eventually merge together. So how do we get one? If we're using GitHub, there are a couple of ways to do it. Here's a GitHub repository for an open source project. If we clone this, our Git utility will automatically register this remote repo. Let's see this in action. First, we copy the clone URL. Now we'll use it as the only argument to git clone. After it finishes cloning the project, we can see if we have any remotes by simply using the git remote command. So let's give it a shot. We'll change into the directory and use git remote. As you can see, we already have a remote called origin. Git allows us to get some more information about this remote, so let's see what it tells us when we use the git remote show command with origin for an argument. The output shows some info about the branch, include the fetch URL, which matches the URL we originally used to clone. So we see that when cloning a branch, we get a remote for free. But what about repositories that we created ourselves locally, like Zach's Problem Solver project? In this case, Zach isn't going to mess around with setting up his own Git server. He's going to host his repository on GitHub. So once again, our journey begins there. Zach has already created a GitHub account, so now he'll need a repository. When clicking the Repositories tab, Zach sees an option to create a new one and clicks the button. Here it asks for a name, so Zach will use the same name that he's been using locally. Here it asks for if you want it to be a public or private repo, and Zach's going to choose public as GitHub does charge a fee for private repositories. Finally, since we're importing an existing repository that already has a README file, he'll skip creating one and just go ahead and submit the form. One of the first things we see on the next screen is the remote URL, or the clone URL. This is what we'll need to link up our local repository with this one, so let's grab it. With this in our clipboard, let's head back to our terminal and link these together. We'll go back to our project directory, and we'll use the git remote add command, and we'll name our remote and supply the clone URL. The standard convention is to name your main remote origin, so Zach will stick with that, knowing that he can rename it at any time if need be. Now that it's added, we should see it show up with the get remote command. And there's the remote that we just added. We're now ready to push our changes, so let's do this with the get push command, followed by the name of the remote we're pushing to, and the branch that we're sending. Get prompts us for our GitHub username and password, as we're trying to authenticate over HTTPS to our GitHub account. This ensures that only Zach or someone Zach names on GitHub will have write access to the repository. We'll talk more about that in a minute. For now, let's authenticate. The output indicates that our changes have been pushed, so let's take a look online. Now you can see that we have files here on our main page. You'll also notice that it shows your commits and branches. Remember, a repository is more than just the latest version of the code. We're in a distributed system, so every repository, remote or local, includes the entire commit history of the project on all branches. Zach is pretty proud of himself, but before calling it a day, there's one more piece of business he wants to attend to. Having to enter his username and password reminded him that there's another secure way to authenticate with Git. As it happens, the option exists to communicate via the SSH protocol, which allows authentication based on registered keys. The first step in this process is to generate an SSH key, so let's head back to our terminal. We'll generate our key using the SSH keygen command, supplying some options, as well as our email address. This will prompt us a few times. First, it will ask us for a file name, which we'll leave as the default, then a passphrase, and a passphrase confirmation. Once finished, the output confirms that the key was generated. We'll need the contents in order to register with GitHub. With that key in our clipboard, let's head over to GitHub, and on the top right of the page, there's a gear icon that opens the settings page. On the left side, we have an SSH keys link, and then an Add SSH key button. We'll give the key a title, and paste in the key from our clipboard, and save it with the Add Key button. Now that our key is registered, we have to make sure our remote is using the SSH URL to push. This can be accomplished with the git remote set URL command. First, we'll need to get the SSH URL. On the right side where the clone URL is, clicking the SSH link causes the SSH URL to appear. So let's copy it and head back to our terminal. And we'll use it as an argument to get remote set URL using origin. Now that Zach has changed the URL, he wants to see if it works. He'll add a simple blank text file that won't cause breaking changes, commit, and push. We'll create a new file in our working directory, add it to the staging area, commit the file to our local repository, and now we'll push. Zach confirms, and his changes have now been securely pushed via SSH using a registered key. For our next video, we'll take a closer look at the history that Git keeps of all its commits. Hello and welcome. We're now wrapping up our second section in this course, in which we've been following our friend Zach as he builds his first GitHub repository. On our last video, we learned how to link remote repositories using GitHub as our host. For our fourth and final video in this section, we'll focus on the commit history, which I think is a great way to demonstrate how powerful Git can be for managing versions of sets of content, whether the items be coding files or any other type of documents. As we learned in the first section of the course, one thing that all version control tools have in common is that they basically tell us a story of how the project was built. Every time someone commits changes, the update comes with a message, author information, and a timestamp, so we know who made the change, when, and why. As an example, consider a program that allows a robot to make a peanut butter and jelly sandwich. As we can see, the history tells us how the program was built. First, we added the ability to retrieve all the needed ingredients and utensils. Then we taught the robot how to spread peanut butter and then the jelly. Finally, the robot learns how to put the sandwich together. In Git, this story is told by the log. One view of this log is available on GitHub if we click the Commits tab on the repository page. What we're seeing here is the story of Zach's problem solver utility in reverse chronological order. Take a look at each commit and notice that it shows the author, the commit message, and how long ago it happened. On the right side, you'll see some alphanumeric characters. This is known as the commit hash and is used to uniquely identify the commit. We'll talk more about this later. First, let's take a closer look at the log in Zach's local repository. We're currently on master in our local repo, so our log should look pretty similar to what we saw on GitHub. Let's view the history using git log. As you can see, we see basically the same information, but it's formatted differently. For example, the commit hash is much longer because GitHub shows a truncated hash. In fact, there are a lot of formatting options you can pass to git log, so you can have the history print out just about any way you can imagine. We won't cover these options here, as this view of the history is sufficient for our purposes. There are many other options besides formatting, though, and we'll cover some of them now. One thing that we might want from a complete history is to be able to narrow our focus. For example, maybe we only want the parts of the story that involve a particular file. We can pass the path to that file as the first argument to git log to accomplish just that. Here we see a slightly different story from before. Some of the same commits are there, but many are omitted because Zach has made many commits where his problem solver class was not modified. Another way to narrow the focus of our story is to view a consecutive string of commits before or after a certain point in the project. Think of this as a chapter in the story, but where you define the beginning and end. There are actually multiple ways to do this, including specifying starting and ending dates as well as commit hashes. For our purposes, Zach has some local commits on a different branch that have not yet been pushed, and he'd like to view the as-of-yet unpublished chapter of his story. The most convenient way to do this is using references, or refs. We haven't really discussed these yet, but we've seen a couple nonetheless. In Git, a ref is a keyword that refers to a specific commit hash in the history. We'll have refs for all of the remote branches we're tracking. We can also make special refs called tags that refer to a release of the project, which we'll discuss in a later video. But perhaps the most familiar ref in the context of our course is head, which refers to the last commit of our current branch in our local repository. We can supply two refs to git log to see the commits that have happened between them, so let's switch to our feature branch and check the difference between origin master and head. First we'll check out our feature branch, and then we'll use the git log command, and as an argument we'll use a range starting with origin master and ending with head. This will tell Git to get the commit hash at the tip of origin master, locate that hash on our current branch, and show us every commit that's happened since then. And that's what we're seeing now. Note that we can verify that this is the case by just checking the commit hashes. If we do git log with no arguments again, the earliest commit hash on our current list should show up immediately above the commit hash that matches the tip of master. Let's see if that's the case. And here's the two commits that we were looking for, right next to each other just as we expected. So far we've seen a lot about how to summarize the history of our project, but Git can tell us a lot more about the history than that. In fact, Git allows us a sort of time travel. Recall that each commit represents a snapshot of the entire project rather than just the changes that were made. This means that we can use any commit hash in the repo as an argument to git checkout, and our files will be exactly as they were when we made that commit. We can do this without having to talk to a remote and without having to undo or replay changes. To understand this, let's take a look at how the Git database works. In this diagram, we see a Git history made up of 3 commits, A, B, and C. In the initial commit, we checked in 3 files, so the database entry for this commit must contain all of them. In the second commit, only the 3rd file was changed, so this entry will contain the updated contents of the changed file, but instead of creating duplicate entries for the other files, Git will add a pointer to the previous commit. Similarly, the 3rd commit only had changes to the 2nd file, so the 1st and 3rd get pointers back to previous entries. With this type of linking in place, when we use the checkout command, Git knows exactly how to change the contents of every file that's checked into the repository to the exact state they were in at the time of the specified commit. Now that we understand what the checkout command is really doing, we're going to do a little time travel. But first, let's see what Zach's problem solver looks like right now. As you can see, Zach's class can solve quite a lot of problems at this point. To demonstrate this via contrast, let's go as far back as we can to the first commit in this project and see what this file used to look like. We can find the first commit hash by viewing the log in reverse. Let's copy the first commit hash in this list and use it as an argument to git checkout. Now our directory should be in the exact same state it was in when Zach made his first commit, so let's see what his problem solver looked like back then. As you can see, Zach's utility was only able to solve really easy problems when he made his first commit. No doubt seeing the difference really brings him a sense of accomplishment, as it highlights how much progress he's made on his journey. In this section, we've learned how to initialize a Git repository, make a commit, manage remotes, and view the commit history. For our next section, we'll be learning features that are essential for team collaboration, such as branching, forking, synchronizing, and issuing pull requests. Hello and welcome to Learning Git. In our last section, we saw how to initialize a repository, make commits, and manage remotes. Today we will begin our third section where we'll learn some features we can use to work collaboratively on a team. By the end of this section, you should understand what a remote tracking branch is and how it's used to get updates from your remotes. For the first video in this section, we'll look specifically at branching and forking. After a brief overview of branching, we'll see how to create a new upstream branch based on master. Then we'll see forking in action, as well as tracking upstream changes from the new fork. A Git repository is made up of different branches of code that all originate from the master branch. A branch is often made to contain the work for an isolated feature. For the feature to be included in a deployed version of the project, the branch needs to be merged back into the master branch, as shown in this diagram. In our last section, we watched our friend Zach create a repository for his new application, make some commits, and push to GitHub. So far, Zach has been working all alone, but he's been looking for collaborators for a new feature he wants to implement, and has finally gotten lucky and found Sarah, a developer from overseas who's interested in taking the lead. Before Sarah can get started, though, she'll need a place to submit her work to. In order to keep her work isolated from other submissions to the master branch, Zach is going to create a new branch on his local machine and push it upstream. This is where Sarah's work will be accumulated until it's ready to be merged into the master branch. One way to create a new local branch is with the git branch command, followed by the branch name as the only argument. Zach will call this branch My Awesome Feature. Since we're currently on the master branch, this will actually create an exact copy of master on Zach's local machine. All that's left to do now is push it to the remote so that it will be available to other users. We do this with the git push command. The first argument to this command is the name of the remote, origin, and the second argument is the name of the branch we want to push, My Awesome Feature. So we submit that, and we see the output in the terminal verifying that our branch has been pushed. Now the new branch of code has been submitted to the remote and should be visible on GitHub. And you can see that the new branch is here in the branches dropdown, My Awesome Feature, ready for some new submissions. At this point, Zach has a couple different options for letting Sarah contribute. One way is to name her as a collaborator, giving her right access to the repository. This can be done on the settings page. On the top left, we see a link that says collaborators. When we click this, we see a search box where you can type in Sarah's name. And there she is. So when we click Add Collaborator, Sarah now shows up on the link. But Zach has some major security concerns with this approach. He doesn't know Sarah, and giving her write access could be a risk. As we'll see in later videos, Git gives you the power to completely rewrite history and erase all traces of a project. Keys to your main repo should be given with great discretion. For now, he's going to remove her from this list. Fortunately, Git allows us another way. You may recall mention of Git's forking workflow from the first section of the course. Git allows other users to make their own online copies of a repository called forks. This way, other contributors can make changes to their own repo and then submit the new commits in a pull request to the original branch, where the changes can be reviewed at the maintainer's discretion. All Zach has to do is make sure Sarah has the link to his repository, and the rest is up to her. Before Sarah can begin working, she'll need to make a fork of the repository, which is really easy to do. Here on the right-hand side, we find a fork button, and when we click it, it will create an exact copy of this repo and place it in Sarah's GitHub account. Let's give it a try. and it's finished. Now that Sarah has the repository online, she'll need to clone it to her local machine with the git clone command. First, we'll copy the clone URL, which can be found on the right side of the screen. Then we'll use the git clone command. This command takes the clone URL as the only argument. Now she has an exact copy of her fork on her local machine, but Sarah also wants to be able to keep her work in sync with Zach's upstream repository. To do this, Sarah adds Zach's repo as another remote, allowing her to pull down any new commits that Zach may make to Sarah's feature branch. She'll do this with git remote add. First, we'll need to grab Zach's clone URL. We'll head back to Zach's repository, grab his clone URL, and now we'll use it as an argument to git remote add. This command takes the name that we want to use for the remote and the clone URL as arguments. So we'll call this remote upstream, paste in the URL, and that's it. Git remote show should verify that we've added the upstream remote. Now she has her own fork of the code where she can submit her work and a link to the upstream repository so she can stay synchronized. She's now ready to contribute. In our next video, we'll see more specifically how Sarah makes use of the upstream link to keep her work synchronized with her collaborators. Hello and welcome back. Today we'll be continuing our third section in this course where we're learning features that are useful for working in a team environment. For our second video in this section, we'll be focusing on how to stay synchronized with the rest of our team in Git's distributed work environment. We'll learn what remote branches are and how we can track their changes. Finally, we'll see how to pull down updates from remote branches. You'll recall from our last video that Sarah has two remote links in her local repository. One is a link to her own fork, which is referenced as origin, and the other, known as upstream, is a link to the repo that Sarah forked from Zach's original remote repository. But what does it mean to have a link to a remote? Essentially, it means that we have a local mirror of each remote repository. This mirror cannot be modified in any way. It is just there so that we can see the differences between the local repo and the remote. Sarah's upstream remote is going to be receiving updates from Zach and any other developer who joins the project. Keeping the mirror synchronized with those updates means pulling down code frequently. Developers should check relevant remote branches for updates on a regular basis to make sure they're modifying the current version of the project. In Git, the term tracking branch refers to the branch that we want to pull updates from. In our last video, Zach created a new branch of code, but if he tries to pull down updates, Git won't know where to get them from. Sarah's going to create a new branch of code on her local machine, but she wants to make sure that she can easily get any commits that Zach makes to the My Awesome Feature branch that Sarah's working on. As usual, there are multiple ways to accomplish this. To make things simple for Sarah, she wants her branch to have the same name as the upstream one it's based on. First, we'll have to perform a git fetch on the upstream remote to make sure that we have all current branches. Now we'll use the git checkout command with a couple arguments. First, we'll specify the track option, followed by upstream / my awesome feature. With this one command, Git has done quite a few things. First, it created a new local branch with the name My Awesome Feature. Second, it set itself up so that when Sarah asks for updates, Git will retrieve them from the upstream version of that branch. Lastly, it moved her into her new branch of code so that any changes she makes now will be staged against her new branch. One thing that's useful to mention here is that our mirrors aren't doing any sort of monitoring of their online counterparts. If Zach makes updates, they will not be immediately reflected in Sarah's local repository. The first thing that Sarah wants to do before making changes is make sure she's synchronized. One common way to do this is with the git pull command. Now, as I was explaining this, Zach has made a few commits, so Sarah has the chance to try git pull out right away. The command is going to do two things for Sarah. First, it will perform a fetch, which will update her remote mirror so that it has all the same commits as the online version. After that, it performs a merge, which means that it will apply those commits to Sarah's local branch. Because we already specified our remote tracking branch, we don't have to supply any arguments to this command. So let's update our local branch. Now we've updated, and you can see that we have a few new commits that Zach has made in preparation for Sarah to hit the ground running. Now let's fast forward to the future, where Sarah has made a few local commits and wants to push them to her remote. So now that Sarah has made some changes, let's see what git status has to tell us about the state of our repository. Take a look at the message near the top, telling us that we are 3 commits ahead of our remote tracking branch. But don't forget that this branch is just a mirror of the actual upstream. If Zach has made more commits, they won't be recorded here. Sarah decides to update her remote tracking branch without applying her changes for now. She uses git fetch to accomplish this. Here we see a list of upstream branches that have been updated since her last fetch, and that my awesome feature is one of them. Now that Sarah's mirror is updated, she uses git status again to see more information. Now the message that once told us that we were ahead of upstream has changed to indicate that we have diverged because the branches have disparate commits. Let's see what this divergence looks like with a diagram of the commit history. This picture shows our branch forking after the last commit. The last commit they have in common is the one that reads second leg of framework, and this is where the branches are said to diverge. This commit was the tip of the branch after Sarah issued the git pull command, but now we have 2 different heads that need to be unified somehow. That means Sarah has to apply these changes. So what happens if she does another git pull? Last time we didn't have any local commits, so the command just fast-forwarded our local branch to match upstream. Things are a little bit different when you have local commits, though. Let's try it out and see what I mean. This command has once again brought the upstream commits into our local branch, but as you can see, it's also opened Sarah's text editor. The text you're seeing is Git's way of asking Sarah to verify or modify the message for the merge commit. A merge commit occurs whenever we perform a pull or a merge in a diverged scenario like this. Rather than adding the commits directly into Sarah's history, a merge commit serves as a link to those commits. This accomplishes our goal of synchronization, but if we do this frequently, it's going to result in a noisy commit history, as we'll have a merge commit every time someone diverges, which happens very frequently in a distributed environment. Let's see what the merge commit looks like in practice. We'll save the default commit message, and Git will apply the merge commit. Now let's use git log to see our history. Now we see the upstream commits that were missing previously in Sarah's local commits, and of course on the top we see a merge commit that ties it all together. Sarah quickly decides she does not want to see these merge commits every time she needs to synchronize. In order to do this more cleanly, we'll use a feature called rebasing, but first we need to undo what we've done with the git reset command. With this we can tell Git to roll back to a given reference or commit hash. Sarah's going to copy the hash of the last commit she made on this branch before the merge and use it as an argument to specify where she wants to rewind. So we take the hash for the call it a day commit, copy it, and then we use it as an argument. This time we use the hard option to git reset, which will not just undo the commits, but will also undo the changes to the files in our working tree. Paste in the hash, and now we are back to the call it a day commit, which is where we were before the pull, and now we're ready to rebase. But first let's see what rebasing means. When you rebase, Git detaches your local commits from the point of divergence, and then it applies the commits from your remote branch on top of that point. Finally, it takes your detached commits and replays them on top of the updates you just pulled. As usual, there are multiple ways to do this, but in this case, the easiest way is once again to use the git pull command, this time using the rebase option. So we enter git pull --rebase. The output confirms that our rebase is successful, and now Sarah has a clean, synchronized branch with some of her own commits ready for submission. That's all for synchronization. Join us for our next video where Sarah will finally make her contribution official by submitting her work for review in a pull request. Hello and welcome to Learning Git. In our last video, we saw how to stay synchronized with the changes that other collaborators make to the upstream. For our third video in this section, we'll be focusing on pull requests. We'll talk briefly about what they are, then we'll see how to make one and how to resolve conflicts. Then, we'll see how to get a good visual representation of our project in terms of its work streams. A pull request is also known as a merge request, which is just what it sounds like, a request to perform a merge from one branch to another. If the request is approved, the changes will be brought into the new branch using a merge commit, as we saw in our previous video on synchronization. To see this in action, let's return to our friend Sarah, who has finally completed a functional piece of her new feature and wants Zach to review it and merge it upstream. Sarah just got finished pushing the changes to her fork, but in order to get these incorporated upstream, she'll need to issue a pull request. Take a look at the message towards the middle of the screen telling us that we recently pushed My Awesome Feature, and to the right of that message, a green button saying Compare and Pull Request. That is exactly what we want to do, so let's click it. Near the top of this page, we see some drop-downs allowing us to choose forks and branches. While we can make a pull request to any branch on any fork, in this case we want to point it to My Awesome Feature on Zach's fork, because the feature isn't finished and we don't want anything merged into master until it is. We also see a message saying can't automatically merge. We apparently have some merge conflicts, which we'll discuss in just a little bit. First, Sarah is going to leave a descriptive title and a brief comment and submit her pull request. She's implemented an engine that can perform a hill climbing algorithm for any problem, so her title and comment should indicate this. Below, we can see a summary of the pull request. It shows how many commits were made and how many files were changed. It also lists all changes for review right underneath. Sarah reviews the changes one last time and clicks Create Pull Request. The request has now been submitted and can be reviewed by other team members. However, notice this message that the pull request contains merge conflicts that must be resolved. What Sarah doesn't know is that Zach has actually added a commit since she last synchronized, and he altered one of the same lines of code as she did. Since Sarah's branch and the upstream branch have mutually exclusive commits, we now have this familiar-looking scenario where the branches have diverged. Git is trying to unify them, but can't move forward because one modification to this file will overwrite the other. Once again, Sarah is going to have to rebase, only this time she'll need to resolve the conflict in the process. As we did in our previous video, we'll use git pull with the rebase option. In the output, we see that we have a conflict. Let's open it up to see what it looks like. What you see here is the result of both Zach and Sarah adding some code to the same place within a file. Git doesn't know what to make of it, so it shows both additions in the file and separates them with some markup, telling you which addition came from where. Head marks the top of the change that came from upstream, whereas Sarah's change is marked at the bottom with her commit message. In this particular case, Sarah wants to keep both of the changes. Now she has the file the way she wants it, so she saves and quits. Note that we just did this resolution manually. There are in fact many merge tools that can be used that can guide you through the conflicts, but without configuring any of those, we can accomplish the same thing with a basic text editor. Now that our only conflict has been resolved, we need to tell Git to add the file that we just fixed. We just use git add with the file name as the argument. Now we can continue rebasing. This signals to Git that Sarah is done resolving conflicts, so it can proceed replaying her changes on top of the updates. Now Git has finished replaying our changes on top of the latest upstream commit. The last step is to update our origin, but because of the rebase we performed, our local branch no longer sufficiently resembles the remote branch, so it will reject a normal push. We'll have to use the force option. When we enter git push, we use the -F to indicate that we are overriding the remote branch with what we have locally. This is followed by the usual arguments, those being the remote name and the branch name. A note of caution here. Sarah has just rewritten the history on her fork. If she mistakenly destroys any needed code that she introduced during these commits, those changes will be lost and gone forever. Use care when rebasing to ensure a non-destructive conflict resolution. Now that we've updated, let's see if our pull request can be merged. Now we see a message saying this pull request can be automatically merged by project collaborators. So let's pay Zach a visit and see what he thinks about Sarah's work. Zach has a look over the changes and all looks well. Going back to the Conversation tab, clicking the Merge Pull Request button will now perform a merge from Sarah's forked branch to Zach's main branch. It asks us for some confirmation, so we confirm, and the pull request is merged. Let's have a look at the commit history for this branch on GitHub. Here's the commit history for the My Awesome Feature branch. Here we see the merge commit on the top and Sarah's commit right underneath it. This page is showing us the branch's commits in a very linear view of our history. It's not very informative to think of our project this way, though. Our project is made of features, and in the workflow we're using, a feature may be made up of many consecutive commits that all get merged at the same time. We therefore get a better view of how our project was built if we can see the commits of these features grouped together. Fortunately, the graph option and the git log command allow us to do that and more. Zach's going to show us just what I mean, but first he'll need to update his local repository to get the new commits he just merged in. Now that we've updated our branch, let's look at our work history with git log and supply the graph option for a much broader view of our project. Notice that the commits are still listed in the exact same order, but now on the left we see some lines. These lines indicate the different branches of code that ultimately converged into the head of our current branch. Each asterisk marks a commit and appears on the line corresponding to the branch it came from. The last asterisk before the line forks in two is the commit that Sarah's branch diverged from. After making some commits, we see the lines come together. This signifies the point where that branch was pulled back into the upstream branch with the merge commit, marked with the asterisk right where the lines meet. This was a simple example, and as more branches get merged, you can expect to see a lot more of these lines. To demonstrate, Zach will merge the feature branch into the master branch and inspect the graph again. First, we need to check out master. Now we'll merge in our feature branch. We'll save the default message for the merge commit and continue. Now let's inspect the graph one more time. Take a look at the two rightmost lines. These match the lines that we were viewing just a moment ago, and the leftmost line represents master. We can see all cases of branches diverging from their parent and being merged back in with merge commits. That's it for today's talk on pull requests. In this section, we have seen how to create branches and forks, how to stay synchronized with our remotes, and how to issue pull requests. Join us for our next section, where we'll cover some of Git's more advanced features. Hello and welcome to Learning Git. In our last section, we saw some useful teamwork features, like branching and forking and issuing pull requests. Today we begin our fourth and final section of the course, where we'll learn a few advanced Git features. In this section, we'll first have a look at interactive rebasing, followed by a video on tagging releases. The last advanced feature we'll discuss will be tracing code, and then we'll wrap it up with some ideas on what to do next with the things we've learned. For our first video, we'll be learning about the interactive rebasing feature. We'll discuss what interactive rebasing is, with a focus on squashing commits. We'll review some of the benefits of rebasing, and we'll also walk through a real-world example showing just how much trouble it can save. So what does interactive rebasing mean? Essentially, it's a feature that allows us to rewrite the commit history. If we want our changes to be modified or repackaged in some way, this feature allows us to make additional changes to previous commits without having to make a new one. There are a number of operations that can be performed on any commit in an interactive rebase. We can change the commit message. We can tell Git to stop at that commit so we can edit some files. Most commonly, though, we will use the squash operation to condense multiple commits into a single commit. This is the operation we'll focus on for today's video. Using the squash operation gives us the ability to combine a range of commits into one with a message that summarizes the entirety of the changes. Another important benefit we get from interactive rebasing is easier synchronization. To demonstrate this, let's visit our friend Sarah, whom we've been following throughout this course. First, let's view Sarah's unpushed commits. We can do this with the git log command if we supply a range of commits as the arguments. The range will start at the tip of upstream my awesome feature, and will end at the tip of our current branch, which is known as head. Here we see 4 commits, and if we looked even closer, we'd see that she modified the same line of code in every commit. The commit messages explain why. With each commit, she was adding an additional argument to a method. She's ready to push it, but she needs to rebase first to make sure her code is synchronized with the upstream. She'll use git pull with the rebase option, and right away we'll see that we have a merge conflict. As we did previously, let's edit the problem file and see what the issue is. Here you can see that Zach has actually modified the exact same line of code. In fact, in our contrived example, he seems to be doing the exact same thing as Sarah, which is adding arguments to a method. Sarah needs to keep all of his changes as the rebase continues, because she needs to make sure that what she ends up modifying is the most current version of the code. So she's going to keep his changes for now, save, and quit. As usual, we add in the file and continue our rebase. Now that we've fixed the conflict and added it back in, it's telling us that there's nothing to do and suggests that we can skip over this step. That's a little bit confusing, but Sarah's going to do as it suggests and see what happens. We use git rebase with the skip option. This tells us to just apply the next commit in the queue. Again, we have a conflict in the same file, so let's open it up and see what's going on. Here we have to fix the exact same conflict, except now we have the second argument that Sarah's added. This rebasing is really starting to get frustrating for Sarah. How many times will she have to tell Git to keep her changes? Interactive rebasing comes to the rescue here. First, Sarah will abort this rebase with git rebase using the abort option. This undid everything, so we're back to where we started. This time Sarah is going to squash all her commits into one. She's made 4 of them as we saw previously. She'll have to tell Git to interactively rebase that many commits. So we use git rebase with the -i option for interactive, and then head ~4 indicates that we're doing the last 4 commits. Now we see the last 4 commits that she made and a list of possible options. In order to squash these commits, she will keep the first one exactly how it is, but for those that remain, she'll replace the word pick with the word squash. This tells Git to merge everything together into a single commit. After saving her changes, the text editor comes back again, giving her the opportunity to choose what the commit message should look like. Since the smaller commits had messages like added argument 1 and added argument 2, she chooses a summarizing message, added arguments. Now she'll save and exit the text editor. Now that we have a single commit instead of 4, let's try rebasing one more time. As we expected, Sarah has the same conflict, but this time it only needs to be resolved once. Now she's going to keep her version of the code, because we're finished rebasing, save and quit. I'm going to add in the file, and continue our rebase, and everything's been applied cleanly. All that's left to do is push and do a pull request. By squashing those commits together, Sarah was able to make conflict resolution significantly easier, and she's also making the Git history a lot less noisy. Join us for our next video where we'll demonstrate how to tag deployments, release candidates, and major production releases of Zach and Sarah's problem solver. Hello and welcome back. Today we'll continue our section on advanced features. In our last video, we saw how to use interactive rebasing to squash multiple commits into one before pushing. For our second video, we'll be learning about tagging releases. We'll talk briefly about what a tag is, and then we'll follow Zach as he tags his first deployment. So what is a tag in the Git world? Well, you can think of a tag as a highly visible bookmark in your project history. It's really just a special kind of ref, not unlike head or upstream master, but those refs always refer to the tip of one branch or another. A tag, however, can refer to any commit in your history, representing a snapshot of your project at the time the tag was created. So why do we care about this? The case we'll focus on today is probably the most common, which is using a tag to mark a deployment. When our code goes live on the internet, we want to know exactly which version of the code is running. While this can be achieved by logging the commit hash at the time of the deployment, tags let us format our deploy history according to whatever scheme we want and assemble that history in a convenient place for us to refer to. To see just what I'm talking about, let's pay a visit to our friend Zach, who's ready to make his first deployment. Zach has just merged in the last of the changes that he's approved for the release candidate. We refer to it as a release candidate because it's going to be deployed to a test server where the features can be thoroughly vetted before Zach releases them to the public. Zach wants his tag to indicate that this is only a release candidate, not an actual release. He may deploy several release candidates before the application passes acceptance testing. When he finally deploys to the production environment, he'll use the tag version 1.0. So for now he chooses the tag name version 1.0 release candidate 1. This command created a local tag pointing at the commit hash at the tip of Zach's local branch. The get tag command with no arguments will show us the tags that we have so far. Here we see the tag we just created as the only item. We can see more information about our tag with the get show command. Here's our proof that a tag is no different than a ref. The output of the command Zach just entered is exactly the same as the output of get show head. As we can clearly see here, this information includes the commit hash, the commit message, and the summary of the changes for that commit. Now that the tag is created, it needs to be pushed upstream. We do this with the get push command using the tags option. Note that Zach is only enforcing a forking workflow for other team members. His only remote is named origin and points to the main repository, so Zach entered get push origin --tags. Now that his first tag has been pushed, let's see what GitHub has to tell us about our tag history. Here we see the tag we just created and pushed. It shows the commit hash that the tag refers to and allows us to download this version of the code as a zip file or a tar. Now anytime Zach needs to know the state of his project at the time of his first release candidate, he can come to this page and find it with ease. That's it for today's discussion on tags. Join us for our next video where we'll see how to trace code to its origin. Hello and welcome back. Today we'll continue our section on advanced features. In our last video we saw how we can use tags to mark which commit was deployed to production. For our third video, we'll learn about some features we can use to trace code to its origin. First we'll see how to find when a line of code was added or modified. Then we'll see how to find the commit where a line of code was deleted. To see tracing in action, let's go back to our friends Zach and Sarah, who have just tagged and deployed their first production release. While Zach was out celebrating, Sarah was keeping an eye on the server logs and noticing lots of errors. They're all coming from the same line of code, so Sarah goes to GitHub to take a look. Since there have been commits to master since the last deploy, Sarah looks up the correct commit hash from the tag for the production release. Sarah will use Browse Files and navigate to the file reported in the error logs. Here's the offending line of code. It's executing a debugging tool that isn't available in the production environment. Sarah doesn't remember doing this and wants to know where this change came from. This is where the blame feature comes in. While it might sound a bit harsh, blame is a way to see who last touched a line of code, as well as the date and commit hash of the change. We can do this from the command line, but conveniently, GitHub provides a button for this, so let's see what it does. Here we see the same file divided into two rows. The left column shows the author, date, and commit hash of all the changes in the right column. Sarah finds the offending line of code again, and sees that it was indeed Zach who introduced the error. Sarah clicks on the commit hash to see the rest of the changes, and takes note of the summary at the top. There is no associated pull request. It looks like Zach was making some late-night commits directly to master without reviewing them carefully. Since he's out partying, Sarah will have to fix this and remind herself to encourage Zach to have his own fork instead of pushing upstream. What we saw works well for finding out who introduced code, but it's not perfect. If the last commit was simply a formatting change, blame doesn't really tell you who introduced the code. More digging might have to be done with git log, which we covered in a previous video. Additionally, The procedure Sarah followed does nothing to indicate when code was removed from the project. Imagine a similar scenario. Sarah is watching the logs and observing errors, but this time the error message indicates that the application tried to access the properties of a null object. This object turns out to be an argument to a method, and Sarah distinctly remembers adding some error handling logic precisely for this case. Once again, Sarah goes to GitHub to view the file in question, and sure enough, there is no longer any error handling for the arguments to the method where the exception occurred. She wants to know when it was removed and why, but the blame button does not reveal that information. If we use blame from the command line, however, we can use the reverse option to accomplish exactly that. But first, Sarah needs to find a commit where the code existed, so she looks through her old pull requests. When we click the pull requests icon, we see a list of all open pull requests. There currently are none, but notice the closed link near the top. When we click this, we see a list of pull requests that have been closed, including those that have been merged. Sarah scrolls through and finds the pull request where she introduced the error handling. There is only one commit here, so let's grab the hash and take it to our command line and tell Git to start looking there for the deleted code. Sarah will type in git blame using the reverse option and will specify a range of commits, starting with the hash that we copied and ending in upstream master. The last argument is the name of the file that we want to know about. The output you see on the screen shows every line of code in the file that existed within that commit range, and next to it you see a hash referencing the last commit where this line of code appeared. It appears that Zach is once again responsible and has some serious explaining to do. That's it for today's discussion on tracing. Join us for our last video to reflect on what we've learned in this course and where to go next with our knowledge and skills. Hello and welcome back to Learning Git, our screencast course on the Git version control system. Today we will conclude our course with a brief overview of topics we've covered along the way and some ideas for what to do next with the knowledge we've gained. We began our course with some abstract discussion about distributed version control and different workflows. These concepts are central to much of what we did in our screencasts. Along the way, you may have noted how the distributed control allowed us to do very useful things, like working and navigating history while offline, or tracking from multiple remotes. You likely also noticed how our project lacked a well-defined workflow. One of our collaborators used a forking workflow while the maintainer pushed his commits directly to the main repository as one would in a centralized version control system. After the abstract, we dove into building a repository, where we learned a lot of things vicariously through our friend Zach. We followed him as he created his problem solver utility and managed his versions with Git. In this second section, we watched Zach initialize his Git repository and make his first commit, then make a remote for it on GitHub. He showed us how to switch to a key-based SSH authentication and also demonstrated some handy uses of the git log command to view the history of changes to the project. Our third section pertained to working collaboratively on a team. For this chapter of our story, Zach has found a team member, Sarah. Zach created a feature branch for her and instructed her to make a fork of the repository and submit her pull requests to the new branch. In these videos, Sarah showed us how to stay synchronized with the upstream repository using the merge and rebase features. We then watched Sarah complete some work and submit her first pull request, also known as a merge request. After merging, we reviewed a graphical representation of the Git history to get a visualization of how the branches diverge and merge back together over the course of a project. After covering the essentials, we reviewed some of the more advanced features that Git has to offer. We used interactive rebasing to squash a series of commits into one, which helped us keep our history clean and also make conflict resolution easier. We also saw how we can create custom refs, known as tags, that refer to a point in the project's history so that we can, for example, keep a record of the versions of code that we deployed to the production environment. Lastly, we discussed Git's blame feature, both in forward and reverse, which gives us an easy and convenient way to see who modified code, when, and why. So now that we know all this, what are our next steps? The answer should be clear. If you have a coding project of your own, put it under version control with Git. Make a remote and invite some other developers to collaborate on your project and watch it grow into your vision one pull request at a time. Or maybe you have an open source project that you want to contribute to. Now's your chance to make a fork. Clone the fork to your local machine and make a pull request to the main repo. The possibilities are many and the choice is yours. Thanks for joining us for our course, and happy versioning.